Hi, today I'm presenting NDN-DPDK file server benchmark on FABRIC testbed. This is joint work between myself and David, and our previous supervisor Lotfi also contributed. So FABRIC is an international research infrastructure. They provide a network testbed with large amounts of compute and storage. FABRIC has 33 sites around the world. Most locations are located in the United States because it's supported by the National Science Foundation. But there are also a few locations in Asia and in Europe. All those FABRIC locations, they are interconnected with high-speed dedicated optical links. All the blue links are 100G and the yellow ones are terabit core network. NDN-DPDK, many of you already know, it is a software implementation of the NDN protocol and designed and aimed at high performance. The main component of NDN-DPDK includes a network forwarder, a traffic generator, and a file server. This is a brief introduction of the NDN-DPDK's file server protocol. It's pretty simple, has only 3 operations, and they all follow the NDN naming convention. To get a file, first you should retrieve its metadata. The metadata is identified by the metadata keyword name component. And the payload of the metadata is the result of StatX system call. It includes the version, the NDN name that you can use later, where the version is derived from the modification timestamp. It also includes the file type, Unix permissions, file size, segment size, number of segment, and all the timestamps that the Unix file system can provide. This format is also compatible with the RDR protocol. In case the file does not exist, when you try to retrieve a non-existent file metadata, the file server will give you an application NAC packet. Once you have the metadata, especially the version name, you can use this version to fetch the file content. And this follows the usual version name component and the segment name component to fetch a segment. The file server also supports directory listing. A directory listing packet is identified by the ls keyword name component. In this benchmark, we will only cover the fetch file content operation, although the file server does support all 3 operations. Before we can run the benchmark, we should first deploy the experiment on FABRIC testbed. The deployment makes use of NDN-DPDK benchmark web application. This is part of the NDN-DPDK codebase, not specific to FABRIC environment, so you can run this benchmark anywhere. The benchmark operation has a topology that looks like this. The benchmark itself is run in a web application which can use GraphQL commands to control 3 instances of NDN-DPDK service. One instance of that service is activated as the NDN-DPDK forwarder, and 2 instances are activated as traffic generators. Each traffic generator contains a producer and a consumer. The producer side is chosen to be a file server. The other option is a ping server, but since we do benchmark for file server, so we chose file server. The file server can access the local file system using IOUring API, that is asynchronous high-performance I/O API. It is provided by the Linux kernel since version 5.2. The consumer side of each traffic generator is a congestion-aware fetcher. This fetcher implements the cubic-like congestion control algorithm. The initial parameters, they are tuned mainly for the low-latency networks. To deploy this on FABRIC, we made a Python-based script that calls into FABRIC's FabLib API, and it will make the topology just like this. As we can see, each producer has access to a NVMe storage device. This is where the files that are served by the file server come from. And they are interconnected using FABRIC's SmartNIC capability. The steps in this Python script is first we create a 3-node slice. Then in each node we download, compile, and install NDN-DPDK codebase. The script can then configure CPU isolation in systemd, reboot the virtual machines to make CPU isolation take effect, and finally enable huge pages that is required by DPDK. The script eventually will upload the environmental configuration. I will show example later, and also start the benchmark web application. In terms of machine specs, the forwarder have access to 24 CPU cores, and the traffic generator machine has 12 cores. In each machine, 2 cores are reserved by the operating system. The others are for NDN-DPDK service. FABRIC provides a lot of different hardware, but the one we care about is the Smart NIC or Ethernet adapter and the NVMe storage device. For Smart NIC, there are 3 options. We can choose NIC Basic. NIC Basic is a 100G Connect X6 device, but we don't get the whole device. We get one of the PCI virtual functions. So this means the 100G port is shared by different experiments running on the same physical machine. We can also choose Connect X5 and Connect X6 dedicated device. The Connect X5 runs at 25G, Connect X6 runs at 100G. These are dedicated, so we get the whole PCI device, but there are not a lot of them. We only have maybe 2, 4, or 6 each on each FABRIC site, so they are less available than the NIC Basic. For NVMe device, FABRIC has a variety of models because they are deployed in different years, but the minimum spec for each NVMe is 1 terabyte of storage capacity, and they support either NVMe 1.2 or 1.3 protocol. Our Python script will format the NVMe to use ext4 file system and then populate the partition with large files filled with random data. This file will be served by the file server. A major strength of FABRIC testbed is there are 33 locations, so we get to pick where we want to deploy the experiment, and we can pick different locations for each of the forward and the traffic generator. In this experiment, we did 3 different choices. We can pick local, which means we put 2 traffic generator and the file server on the same location. They will still go through the Smart NIC and the Ethernet switch, but they don't leave the rack. We can choose near. We put the forward and 1 traffic generator in one location and the other traffic generator in another location that is adjacent to the forwarder. This simulates an interstate or maybe just across one state line. Those kind of transfer. Finally, we can pick far. We put first traffic generator in California. We put the forwarder in Illinois, and we put the other traffic generator in Maryland. That's a cross-country file transfer. Once we made the selection of the locations and also the NIC model, we run the Python script. At the end of that script, it will show you an environment file. The environment file contains things like a PCI address and the MAC address of each Ethernet adapter. Those will be used by the benchmark web application to deploy the benchmark. It will also show you a command line. It allows the experimenter to access the benchmark web application. So with that, we have the experiment deployed and we can run the benchmark. This is the interface of the benchmark web application. It has a lot of parameters, but important one is here we chose to use 8 threads on the forwarder. We chose to have file server as a producer and with 2 threads in the producer. We also pick we want 48 files, each has 32 gigabytes. This means the total transfer volume would be 3 terabytes in both directions. Then we press that start button. The benchmark web app uses GraphQL to start the forwarder, start the file server and the fetches. Then it can gather and show the statistics in this table. It will run continuously until you stop it. So we did 5 runs for each of those combinations, different NICs and different location choices. And we report the average here. The main metric is duration, but the data packet throughput, excluding interest and excluding the retransmission, is derived from that. We can also calculate the content payload goodput in terms. So the best result we got is 76 gigabits per second. That's for a disk to memory file transfer in the local location. This table shows the same thing, but we can look at the curves and see the trend. Regarding NIC basic, the shared NIC, and the Connect X6, the dedicated NIC, they have really similar result. This really means not many people were using FABRIC at the moment I did those experiments. For the 25G Connect X6 port, the port speed would be a bottleneck. So because my app is running faster than this port, but if we do a cross-country transfer, then all the throughput are lower, and it doesn't matter which port size I pick. This means the network can have congestion, or it's just because my factory parameters are not tuned well for the high latency networks. So that's all for the FABRIC experiment, but let's pull back a little and talk about the file server protocol. So the file server protocol has more than one implementation because it's supposed to be universal. So the protocol is compatible with NDN cat chunks we mentioned in the tooling talks this morning, and so this means we can use NDN cat chunks to retrieve a file from the file server. It's also implemented in NDN-DPDK, in NDN-Go, NDN-TS libraries, as well as the NDN-C codebase from the NIST project. The server side is implemented in NDN-6 file server, and also implemented in NDN-DPDK. And for the upcoming hackathon, I also propose a project to implement the file server protocol server side in NDN-D codebase. The file server has a few deployments already. First is the NDN testbed, specifically the testbed status page. The information there are actually retrieved from NDN-6 file server running in the testbed routers. Then I have a demo site for NDN-TS adaptive video. Those video clips are also served by the file server now. On this project, they are publishing genomics data using the NDN-DPDK file server. And finally, we have been running NDN testbed traffic traces with collaboration with Tennessee Tech. Currently, the traffic trace files are distributed through GitHub LFS, but we are running into quota issues. So we are planning to move the traffic traces, host them with HTTP and also NDN file server. Finally, it's a quick update on the NDN DPDK codebase, since it's been 4 years since I last presented this. So in the forwarder, we expanded the hardware offload for the Ethernet adapters. We also enhanced the test coverage. In the interactive benchmark web application, as I showed earlier, it now supports the file server in addition to the pin server. And also we added some user-facing documentation. Thank you. Here are some links, and please ask questions.
Thanks, Junxiao. Let's see if there are any questions.
So for the file server protocol, I wonder if it is read-only or does it support uploading or modifying a file?
The file server protocol is read-only. I cannot write to it because that would require security. It's a lot more complicated. But in my dissertation, I have another file server protocol that can support writing. It can be adapted here.
I see. Thank you.
Right. It would be a lot more complicated, but a lot more interesting, of course. And then that comes the question of what would be the difference or discriminating factor between the repo and the file server.
The repo, you have to pre-chunk the files and produce the signature, everything. This really means on the server side, you are storing the same thing twice, one as data packets, the other as files. We all know Jeff Burke group did a thing called the NDN-FS port. It's their way. You have to copy all the file to create the signatures. But my file server protocol or the protocol actually doesn't matter. All the implementations, it just read from Unix file system.
From Unix file system, you convert it in packets?
Yes, it's converted on the fly. Yeah, it also means that it will be signed by the file server. It's not signed by whoever wrote the file.
I see. And that overhead is affecting your results or no?
Not really. NDN-DPDK's file server doesn't do the real signing. It just gives you a signature type 200. It doesn't contain a signature. Then for the NDN-6 file server, it will follow NDN-CXX default keychain. But my argument is I sign it once. As long as it doesn't change, the content still should satisfy subsequent request.
So in your measurement, where is the bottleneck?
It's the network, since the software is not a bottleneck. Oh, and this test is without writing to disk, but the feature API now supports writing to disk, but the benchmark does not do that. And the writing is IOU ring, so it will not block much.
So this is measuring the network side of things, not the I/O, disk I/O, things like that. So just a small question on the client. The client's compatible with the protocol. So since you talked about this listing feature, do these clients, which of these clients support listing?
Listing, NDN-C, I don't know. Oh, yeah. The NDN-DPDK feature does not support listing. So cat chunks, you can do listing. It's the same. You just put ls keyword there. It will show you the payload of the listing. And the NDN Go one and the NDN TS, they all have API for listing. They are not binary. They are just API.
Thanks.
Thank you, Junxiao.